Okay, so last class we had started to talk about graph algorithms, and in particular we had started to talk about breadth-first search, which was a way of traversing the graph so that we visited every node officially once and every edge at most twice. Okay, actually twice. Once coming in, once going out. Okay, and so therefore the traversal, walking over the graph, was order n plus m. And we saw that the tree of discovery had this marvelous property that if it was an unweighted graph, the discovery tree gave you the shortest path from the source to every other vertex in the graph. Any questions about any of that stuff? Okay, good. So let's take a look at this. It says basically, asks to prove that if you do a breadth-first search on an undirected graph, every edge is either a tree edge or a cross edge, where a cross edge means an edge that is neither an ancestor or a descendant. Okay, where x is neither an ancestor or a descendant. So what does this mean? We should agree that the parent relation in a breadth-first search, if we do breadth-first search, there is going to be a tree of discovery, okay, of vertices. Does everybody agree with that? And this would mean if this was our source, the number of hops up here was the smallest number of what you call it, hops it would take to get to the source. Now, if we have an n-vertex graph, how many edges are there in a tree on n vertices? N minus 1. Does everybody agree that the number of tree edges in a graph is going to be n minus 1? What happens to the rest of those edges? Okay. Okay, what happens to the rest of those edges? Okay. Well, they are going to be edges that didn't discover something, but happened when we explored vertices. Does everybody agree with that? Now, we can still say we're going to be, it pays to classify these edges into what happened the first time we visited that edge. Recognize we're going to visit an edge both coming and going. Okay? What are the kind of properties that this says? It says that every edge, okay, is either a tree edge or doesn't go to a node where it is an ancestor or a descendant of it. Okay? Why couldn't there be an edge like this? Okay? Where these are the tree of discovery edges, but when we were exploring this vertex, one of the edges happened to go to this vertex, right? In this case, this is something that's not a tree edge, and yet it goes to an ancestor, it goes to a descendant. Why is that not possible? Yes?
It's not possible because with breadth-first search, you're basically discovering every single adjacent vertices towards that vertex. So if it really was connected, the position wouldn't be down there where just one level.
It wouldn't be here. Does everybody see that? That if this edge existed, when we were exploring this vertex under breadth-first search, what would have happened is this would have, the tree would have looked like this. There would have been another vertex here, and the edge that went from this vertex to that vertex would no longer go between an ancestor and a descendant. Does everybody see it's going to brothers now, between brothers now? Does everybody see that? So the breadth-first search, the fact that we did breadth-first search, gave us a tree of discovery, which had nice properties. But it also lays the edges out in a nice way. That is kind of an important thing. And depth-first search is going to lay out the edges in an even nicer way. That's why we're going to care about depth-first search eventually. Any questions? Yes? Is that a proof? I think that is a proof, remember, is an argument that convinces somebody. Right? So we take a vote and we decide whether people are convinced. Okay? Does everybody agree? That is basically the argument, that it's sort of a proof by contradiction. How do you prove things? You can prove things by induction or contradiction. What is the contradiction? You're saying, no, 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 no. Here is a graph and a start and a breadth first search where there is in fact an edge to its descendant, an edge that goes to a descendant. Okay? That's not a tree edge. Well, what is the contradiction? No, because it would have been a tree edge if it came from here. Right? Does everybody see that? And what if we first saw the edge here? Is it possible we would have first seen the edge here? So it was a back edge? No, because we would have explored this edge up here. And it would never have not be the case that we would have seen it for the first time there. Okay? So if an edge isn't in the tree, and it can't go to an ancestor or a descendant, where can it go? It can be a cross edge, basically, where it's never an ancestor or a descendant. Any questions? Yes? A tree edge is one that was involved in the discovery. So a tree edge is whenever we declared, remember we had this parent array last time when we talked about breadth first search. Any edge that triggers action in the parent array is a tree edge. Okay? And that tree of discovery is what made shortest path on unweighted graphs work from breadth first search, right? We had that parent array, that was the tree of discovery. And the claim is that any edge in breadth first search that is not a tree edge has to be a cross edge. Any questions? Yes?
Are there any other types of edges we should be aware of?
Okay, so you should keep your eyes out for tree edges, back edges, which are edges that go from a descendant to an ancestor, forward edges, which go from a elder to a descendant, okay, and cross edges are generally speaking the rest of them. Sometimes we're going to be concerned a little bit about breaking the cross edges up further, but for now, does everybody see this kind of idea that when we do a traversal, we are labeling every edge implicitly? We build a tree, and every edge gets a label that is unambiguous. Yes?
Doesn't that break the definition of a tree if their cycle exists?
Okay, does that break the definition of a tree? The answer is no, because the tree edges don't have any cycles. Recognize what I said. You had n vertices in a graph. You have m edges. Only the elite n minus 1 of them get to be called tree edges, right? What are the rest of them? They've got to be called something, right? And in general, what can they be doing? Once the tree is established, I claim the following breakdown of edge types is complete. Either an edge can go to a descendant. See how this edge is going directly to a descendant? That is called a forward edge. An edge could go back to an ancestor. That is called a back edge. And for purposes now, and probably purposes for what we really need, anything that is not a tree edge, not a back edge, not a forward edge, is a cross edge. Any questions about that? Yes? An ancestor could be going back to the parent, although since you're visiting each edge, since you're labeling each edge once, basically the first time you see it, if it goes between you and your parent, it was a treatise edge, right? So it can't go back to the parent, but it can go back to your grandparent or your great-grandparent or great-great-great-grandparent, ... Any questions? Yes? Are all tree edges forward edges? The answer is no, because they're tree edges. Okay? That's kind of, again, it's not, that's the classification we're going to find useful. Okay? Edges are going to be, in fact, again, I'll have a slide about that later on, just to prove I'm not making this up on the fly. Okay? Basically, the kind of edges that we're going to care about Again, this is going to be more important for DFS even than it is for BFS. But basically, every edge, n minus one of those edges are going to be tree edges because they are involved in discovery. They discover vertices. If you have an edge that goes back to an ancestor, if the first time I process this edge is when I'm looking at this vertex, then it's a back edge. If the first time I processed that edge was when I was at a root node, then it would go down to a descendant, and that's what we call a forward edge. And anything that doesn't go to an ancestor or a descendant and is not in the tree, we're going to call a cross edge. Any questions? Yes? Well, what is true is, let's stop and think about it. The word spanning tree was just evoked, okay? How many people here have ever heard of spanning trees? How many people have ever heard them in anything except a minimum spanning tree? Okay, no. Minimum spanning tree is a weighted graph thing we're going to talk about later. But what is a spanning tree? A spanning tree is a set of edges that connect all the vertices, with a minimal set of edges that connect all the vertices, which means any subset of n minus 1 edges that connect all the vertices, right? That's what a spanning tree is. And what you're saying is, gee, the breadth first search tree, the tree nodes in the breadth first search defined by that parent thing, form a spanning tree of the graph. Does everybody agree with that? Okay. That's one reason why these BFS trees and DFS trees are going to be so valuable, because they do form spanning trees of graphs. Okay. We're still in the unweighted graph world. Okay. But any questions about that? Okay. Any questions about this? So, the important thing to understand the subtleties of depth first search and breadth first search is to realize that what we are talking about are the discovery points represent trees, a tree. Every other edge can be classified as either being forward or backwards or cross edge. Based on, once you have labeled the tree, you show me, draw that edge when you discover it. Which way did it go in when you discovered it? It classified what you did. Any questions? Okay. And just to muddle the waters a little bit, let's get back to our spanning tree a little bit. Let's say that we were in a breadth first search tree. Here was our breadth first search tree, right? We agreed it couldn't have any back edges. We agreed it couldn't have any forward edges either, right? Could only have cross edges. Can cross edges go any which way in a graph like this? If it's an undirected graph, can we have a cross edge between any pair of vertices here? Or is there maybe a little bit more structure than that? More structure. What kind of more structure do we have? Could we have an edge that went from this? Let's think of, could we have an edge that would go from this vertex to this vertex? Does everybody see that? See what happened? Is it possible that we would have an edge that went from here to here as a cross edge? Who here says yes? Who here says no? Okay, the yeses have it. Okay, why is that? What happened? Well, actually, is this possible? The answer is yes. Yes, it is, because what would have happened? Remember, breadth first search processes edges in oldest first, right? So, bung all the neighbors of this one. Then this was the oldest one. Bung all the neighbors of this one. Bung all the neighbors of this one. This vertex has already been discovered, right? But there's no reason why the first time we saw that edge couldn't have been this way. Does everybody agree with that? What about if we turn the arrow around? Is there any way that we could have a cross edge where this vertex was discovered here? It's undirected. The graph is undirected. That's 100% true. But the interpretation here is indirected. Goes from from the one that is processing it to its neighbor. Right? We're going to visit each vertex. We're going to interpret it the first time we walk down it. Okay? Is it possible that the first time we visited this edge that went back to the previous level, is it possible that this was the vertex where we first saw this edge? No. Why not? Because this was an older vertex, right? So this is not possible. Does everybody see that? What about a cross edge that went like this? Here's another cross edge. Could we have a cross edge that went from this vertex to this vertex? No. Why not? It's because this one you're saying is older than that one. It's a shortest path spanning tree, basically, right? The shortest path, if there was more than one level between it, that meant this vertex would have been discovered by when we explored this edge vertex. Does everybody see that? So we can have cross edges, but the cross edges can't span neighboring levels if we have a breadth first search tree. Does everybody see that? And so one of the cool things about breadth first search, which is going to warm us up for depth first search, is that the course of the search labels the edges. Okay? Any questions? Any questions about that? Okay. So what I wanted to do now is to talk about two applications that are very, very important, okay, of breadth first search. It turns out depth first search can do both of these also, but let's talk about them as breadth first search. And one of them sort of was already discussed today. We talked about we mumbled the word spanning tree, right? One problem that is very important is trying to find all the pieces of a graph where there is no connection between pieces. Okay? So let's take a look at this. If we have the following graph on 6 vertices, here I'm going to draw one. How many pieces are that graph? Okay, so everybody look at that graph. How many pieces do we have there? How many people say 2? Raise your hand. Okay, how many people say 1? Okay, it's 2 pieces of this graph. From this piece you can go to walk, walk, walk. Okay, from here you can walk, 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 walk. Okay, but does everybody see that there are 2 separate chunks in this graph? Now, by looking at the picture, maybe you can tell that there's 2 pieces, right? But does everybody see that looking at an adjacency list of this thing, it is not immediately obvious that there's 2 pieces here? Does everybody get that idea? Counting the number of finding how many pieces there are in a graph and which vertices belong to which piece turn out to be very, very important problems. Okay, they're very, maybe the simplest real application of depth first / breadth first search is to find how many pieces there are. What would the connected components of the road network look like? Okay, if we took the road network of the world, what would the connected components of that be? Yeah, continents. Okay, probably there's islands that fall off of continents also, right? Because everybody. Probably not continents. I think North America and South America are probably connected by roads, right? But Australia would certainly be off. Certainly isolated land masses have got to be it, right? So figuring out how many pieces a graph is in and which vertices are in what piece is a very fundamental problem. Okay? Any questions? Now suppose I give you a vertex. How would I figure out in a graph? Let's say I start out with here. How can I find out what vertices are in the same piece as this vertex? Okay. How would we figure that out, given what we know, yeah?
Do a tour from that node.
If we do a breadth first search from that vertex, what's going to happen? We're going to start here. We're going to discover this guy. Discover this guy, discover this guy. There's no place left to go, right? Our spanning tree that we're going to build of discovery is going to look like that. Is that right? And then it's going to end and come back. Okay? And what does that mean? Everything that is reachable from this in an undirected graph is going to be the vertices in the same tree. Does everybody see that? The breadth-first search, if it tells me the shortest path to every vertex, it'll tell me exactly how far it is, everything I can reach. I will never find these other three vertices in that traversal. Does everybody see that? So how do I find connected components in a graph? Basically, anything that I discover in a breadth-first search must be part of the same component. If I then repeat it from any undiscovered vertex, I will find the next component. Does everybody see that? So what does a connected components algorithm look like? This is an algorithm to find the connected components of a graph, or how many connected components, and depending upon how you instrument what it is you do when you visit a vertex, it will also print out what component the vertex is in. But what are we going to do? We're going to initialize our traversal. Okay? We're going to set every vertex to be undiscovered, which is what we started out our breadth-first search in, right? Then for I goes from 1 to n. If vertex I is discovered, okay, is not discovered, then that means we have a new connected component, right? Originally vertex 1 wasn't discovered. We're going to set our number of components to be one more than it was. Print out now we're at we're in component 1, and do a breadth-first search from that. That's going to go through and do everything to all the arrays. Among other things, it's going to discover certain vertices and then mark them as fully processed. Is that right? Now we're going to go around for a second time and say, is vertex 2 discovered? If vertex 2 was discovered then, well, we're going to move on. Is vertex 3 discovered? Yes. Vertex 4 wasn't discovered. We start doing another traversal. Does everybody see this? So this loop is going to go around n times and call BFS potentially whenever it is undiscovered. Any questions about that? People see how the algorithm works? Now use your thinking cap for a moment. If we have a graph on n vertices and m edges, what is the running time of this algorithm in the worst case? Okay, does anyone want to make a proposal? Okay, you see the algorithm. How much time does... Okay, yes? What's your proposal?
I think O of n, because every time you discover an edge, it's charged a vertex, it's charged to that vertex.
Okay, you want to say order n, okay? And n isn't going to be the right answer for the following reason. Do we agree that if we have n, a graph with a large number of edges, more than n edges, do we have to visit every edge to figure out whether or not it's connected? Suppose there was one little island here and these n-1 other vertices, everyone was connected to each other. Don't you see you've got to do your search potentially visiting all the edges? So it's not going to be order n. Does anyone want to make another proposal for what this is going to be? Yeah? Order m? Do we think it's order m? I hear no. Why is it not order m? What if we have a world where everyone is an island? What is m here? How many components do we have to print out? N. Okay, so it's certainly not order m. Yeah? You're now boldly saying n plus m. Now, why is it n plus m? Let's think about this, okay? How much time does a breadth-first search on an n-vertex m-edge graph take? How much time does that take? If you have a graph with n vertices and m edges, How much time does breadth first search take? N plus M. How many people realize that? Raise your hand if you know that. How many people don't know that breadth first search takes N plus M time? Okay, we showed that last time. Okay, why was it? We had an adjacency list. Okay, what were we going to be doing? Breadth first search starts from a vertex, basically is going to explore every outgoing edge here, right? It's going to do a constant amount of bookkeeping for a vertex. Then there was a data structure, a queue, to maintain what the next thing we had to do was. Every vertex is going to get processed once. Every edge on a list is going to be walked over, coming and going. That was N plus 2M, or order N plus M. Any questions about that? This you got to know. There's a few things I'm going to make sure you got to know. That's one you got to know. Why is breadth first search order N plus M? Any questions? Now here's the tricky part. If this breadth first search can take order N plus M time, why, if I stick it in a loop that's going around N times, why are you still saying it the total amount is N times N plus M rather than N times N plus M? Yeah? You're only doing stuff on any traversal with the stuff in the component. Does everybody see that? Let's get back to our Jewish star graph here, right? Suppose, let's say, we had a giant component out here, okay, with 1 billion vertices and 2 billion edges, okay? How much time is this breadth first search going to take here? No matter how much other stuff I've got in the graph, how much time does that take? Yeah. You know, it's 3 vertices and 3 edges. Does everybody see that? And when I do the next traversal, it's going to pick up the other stuff. Does everybody see it? It's linear in the total. Each search is linear in the size of its components. The number of vertices and number of edges in the graph is the sum of the number of vertices in each component and the sum of the number of edges in each component. Does everybody see that? So the truth is, this is going to still run in order N plus M time on any graph, regardless of how many components it has. Any questions about that? A question like I don't see it is a good question. Any questions? Okay. A question like, what pages in the book should I read about this if I'm confused about it? Is also a good question. Okay, although you should be able to figure that out from a copy of the book. Any questions about that? Okay. So the interesting thing, this is an important application of breadth first search, right? And there are a lot of a surprisingly large number of problems that reduce to, given a graph, find the connected pieces of it. Okay? For one thing, if you try to find the minimum spanning tree of a non-connected graph, your program will run forever, right? Because there's no spanning tree that connects it, right? So what you typically want to do is take your graph, find the separate connected components, and work with each separately. That's one reason why connected component is an important problem. There's a bunch of problems that just turn out to be finding a surprising number of problems were reduced to, given a graph, find how many components is, or tell me whether it's connected. Like, how many people have ever solved Rubik's Cubes? Okay, some of you. Now, if you take it, you may have known that if you took when Rubik's Cubes first came out, some companies started selling stickers for people who were stuck with their Rubik's Cube that would have colors, and they could just plaster them on the cube to redo. Okay? Now, if you randomly color each node of the Rubik's Cube, is it necessarily solvable? And the answer turns out to be no. Now, how could you prove that? Well, you could build a graph where the vertices are the states of the Rubik's Cube. Okay? And you would have an edge between any two states of a Rubik's Cube if there was a way to turn one of the wheels and get from that state to the other. Okay? If you believe that, then there was a desired ending state, which was the state where they were all colored neatly on a side, right? And the question of, is it possible to solve it from any position, asks whether all the positions are in the same connected component as the end state. Okay? And it basically reduces to testing whether a graph is connected. Any questions about it? So connectivity, you file in your head that connectivity is something you can do easily, and it's a good thing to know about. And somewhere in your life, you will have a graph that is, testing connectivity will turn out to be really the game that you want to solve. Any questions? Okay. Let me give you one other application of breadth-first search that maybe is going to be a little, is also enlightening, which has to do with two coloring, okay? So a coloring of vertices is an assignment of labels or colors, labels either from 1 to the number of colors, or you can call them white, red, pink, whatever you want to do it, with the property that after we have colored the vertices, no edge links two vertices of the same color. Okay? We say that a graph is bipartite if there is a way to color it without conflicts using two colors. Okay? Any questions about that? What is an example in the world of bipartite graphs? Graphs that arise in an application that you can think of that have the vertices can in fact be put into two categories, such that all the edges cross categories rather than staying in the same category. Has anybody ever encountered a bipartite graph? Yeah? In a red-black tree. So in a red-black tree, which you took your data structures class, you may have learned that, hey, those were trees that were colored. What is interesting with that is an argument that a tree is a bipartite graph. That's really what you're sort of saying. If you take a look at any tree, let's take a look at this tree. If we color this tree node black, what color do these nodes have to be? Red, or I'm going to call them white because I like white and black better, okay? If this node is white, what color does this node have to be? Well, if we're going to color it with two colors, it can't be white, so it's got to be black. Does everybody see that? And does everybody see that because there is no cycles in a tree, we can push this problem down, and every node is going to be either white or black, and there's never going to be an edge contradicting that. Yeah?
Aren't there edge cases in red-black tree implementations where you have...
Okay, red-black trees are complicated things. I didn't come in here talking about red-black trees, okay? I mean, but the key point that I do want to make is it should be clear from this argument that every tree is an example of a bipartite graph. That much should be clear, okay? And I think that any questions about that? Any other things in the world that are bipartite that you guys know about? Okay, yeah?
Car ownership, because people can own cars. Cars can be owned by people. People can own multiple cars.
And mercifully, people can't own people, right? Okay, so if we have an ownership graph where one kind of thing are vertices and one kind of things are property, okay? There is an edge. Everything is owned by a person. Does everybody agree that that is a bipartite graph? And so that can be colored with two colors, okay? Turns out in a lot of cases there are efficient algorithms on bipartite graphs where they're not efficient algorithms on more complicated graphs. So being able to tell whether a graph is bipartite turns out to be a good skill to have. For example, testing whether a graph can be colored with three colors. That's going to be an example of one of our NP-complete problems. There's no fast algorithm to tell whether you can color a graph with three colors. But there is a fast algorithm to tell whether it can be colored with two colors. So how would we tell whether a graph is colorable by two colors? What would be the idea based on what we've seen so far? Yeah? Right, so basically what you're saying is start from one vertex. Whenever you have a new vertex you discover, a neighbor that hasn't been colored before, Color it the opposite color. Does everybody agree with that? What if you have a neighbor that has been colored before? Well, you'd better hope that it's colored a different color, right? If that neighbor's been colored, again, a tree, it's very simple. But we could also imagine other kinds of edges in this graph, right? There could be an edge from here to here, from here to here, from here to here, right? Okay? The question is, if when we color a vertex, we have a white vertex, we discover a neighbor that's black, that's white, we're in trouble. If we have a black vertex, we discover a neighbor that's black, we're in trouble. If we are a black vertex and we discover a neighbor that's white, that's fine. White vertex, discover a neighbor that's black, that's fine. Either way, discover a vertex neighbor that is uncolored, color it a different color. Does everybody see that? Yes?
So if this seems like a greedy algorithm that starts somewhere and then just sort of tries to basically breadth search. If this fails, does it mean that there is no coloring?
If it fails, it means that there is no coloring. You have a contradiction. Okay? So what are we going to do? How is my two-coloring algorithm going to work? Well, originally, color every vertex as uncolored in the graph. Then, to cover for the fact that I can have disconnected components, I'm doing this trick for all vertices. If vertex I has not been discovered, let's start a search from it. For the first vertex in my component, I chose arbitrarily to set it to be white. I'm then going to do a breadth-first search on that graph. And as you remember from my breadth-first search implementation, I had these routines that say process vertex, that basically, and process edge, that would tell you you have a chance. It's the first time you've seen that vertex, the first time you've seen that edge. What do you want to do with it? Okay? And to make my breadth-first search do by two coloring, I am going to say if I have an edge that goes from x to y, I am going to ask, is the color of x the same as the color of y? If the color of x is the same as the color of y, then I'm in trouble, right? I've discovered a contradiction. Okay? If so, okay, the graph is not bipartite and I'd better emit an error message. Otherwise, what should I do? If the color of that vertex is not the same as me, I should recolor it if it is still uncolored, or it is harmless for me to color it anyway, the opposite color of what I'm doing. Does everybody see that? Because there's not really a contradiction. Okay? So I'm going to recolor it. If my color was white, the complement color will be black and vice versa. Okay? And it's going to return that there. Any questions about it? Yes? So what am I saying here? In the way I implemented it, perhaps slightly sloppily, but in a harmless case, let's say that this vertex here, this vertex is black. What color is this vertex going to be? White. Suppose another vertex comes along, and I look at this edge coming out of it. What color is this vertex? If it's white, I've got a problem. Does everybody see it? If not, it's got to be black. And can I color this white vertex the opposite color? What was the opposite color of black? Just painting it white again. Does everybody see that?
So you don't change the color.
In this case, I'm repainting it, but I'm not changing the color. Okay? I could have, if for some reason you're saying, my God, you're using so much paint. What could I have done? I could have said, well, if Y is uncolored, then paint it white, if you're concerned about how much paint I'm using. Okay, but otherwise, this is correct. Does everybody see that? Any questions about that? Any questions to see about why this two colors a graph? And does everybody see the amazing power that comes from having a breadth-first search where I've got these stubs that let me say, what do I do when I visit a vertex, or what do I do when I visit an edge? Because the key to making graph algorithms do something interesting. No one pays you to do a traversal. They pay you to do a traversal when you do something at each vertex or edge. Okay? And so most graph algorithms reduce, a large class of graph algorithms reduced to just what do you do at the vertex or the edge when you see it. Any questions about that? Any questions about connected components or two-coloring and how they are really easy once you have the idea of a breadth-first search? Any questions? Okay, good. So let's talk about another type of graph traversal, which in some sense is breadth-first search with one change of a line. If you went back to my breadth-first search implementation before, remember when I said there was a thing called a queue I defined to hold all the vertices that we've discovered but not yet processed? If I change that queue to a stack, woof, I've got depth first search. Okay? In some sense, the only difference between a breadth first search and a depth first search is whether I store these things in a queue, which pulls out the oldest vertex first, versus a stack, which pulls out the newest vertex first. Does everybody see that? So in a depth-first search, whenever I discover something, my attention span has shifted. Does everybody see it? I'm going to stop what I'm doing and go do that. Go do that. Anything I discover, I'm going to look around. Is there anything else to discover? No. I'm going to go back to the previous thing that I was working on. Okay? So here, there is also, I find it easier though, instead of thinking about depth-first search as breadth-first search with a stack, I find it easier to think of a recursive implementation here. Because if you think about it, stacks are what made recursion go. Did you guys learn enough about how programming languages are implemented to see the connection between stacks and recursion? How many people know about the connection between stacks and recursion? How many people don't know about it? Okay, a few. Okay, no, well, a few. Okay? Basically, what happens when you make a recursive call in a program, the runtime system keeps track of where you were and jumps to the new call. And it does its thing, and once it's finished and it exits, it goes back to where it was. And it stores these calls on a stack. Okay? So there is a big connection between recursion and stacks. And so there is another way to write recursion, write depth-first search, that basically doesn't use an explicit stack, okay, but it uses recursion instead. So what is depth-first search now on a graph? Okay, you see I'm not storing an explicit stack. I'm not recursion deal with that. But what is the basic idea? If V is my starting point, I've discovered it. If I want to do something with this vertex right after discovering it, now's a good time. Otherwise, what am I going to do? While, the neighbors of me, my neighbors are not nil, meaning I'm going to cruise through the adjacency list of V, and look at all edges V go to Y. If Y has not been discovered, that's great. I've discovered it, right? So who's the parent of Y? V, because it was edge VY that discovered it. Okay? Now, if I want to do something with that newly discovered edge, I'll call process edge. And before I go anything else, I'm going to recursively go from the newly discovered vertex. Does everybody see that? And go explore all that out before bombing up to here. Any questions about that? Okay? And if it didn't discover it, well, I still have to process the edge. So let me go process the edge and keep doing this over all iterations. And then once I have looked at all the adjacency lists of me, then I will have discovered, I can then process the vertex late if I feel I want to do something then. Any questions about that? It's the same basic vision as breadth-first search, except that instead of processing a vertex completely before moving on and working with the oldest one, Whenever we discover something, we immediately shift our attention there. Any questions about that? Okay. If you look carefully at my code, there's something a little different that I'm doing, however. Okay? Or I'm keeping some extra arrays that are helpful. I am keeping a time array, an entry, a time in my search, and an entry and exit time. You can kind of think that there is a moment in the search where the vertex is discovered, and there is a moment when the vertex is completely processed. When it is discovered is the entry time. When it is completely processed, it is the exit time. And because of the nature of breadth depth first search, these turn out to be useful concepts to keep track of. Any questions? Okay, any questions about depth first search? Okay, fair enough. Now, what is it that makes depth first search interesting and powerful as an algorithmic thing? Okay? Again, any data structure we use to store the queue, the remaining vertices would come up with a different order. But depth first search has a very interesting property to it. In breadth first search, we said that everything was either a tree edge or a cross edge. In a depth first search of an undirected graph, every edge is either a tree edge or a back edge to an ancestor. Okay, think about this for a while. Why is it that we can't have, if it was an undirected graph, why couldn't we have a cross edge? Why couldn't there be an edge from here to here? Okay, where this, in this particular graph, why couldn't there be a cross edge here? Well, think what was going to happen. We started on this vertex. I discover an edge to 2. Ooh, great, now I've got 2, right? I would go down to, I discover 3, I shift my attention, and there I discover 4, there I discover 5. There the only other edge goes back here. If there was an edge between 2 and 6, how would the tree look different? Does everybody agree that when I get back from my recursion call and start processing this one, 6 is going to be a descendant of 2? How many people see that? Okay? So the interesting thing is we could, if there was an edge from 2 to 6, okay, when we explored, actually to be precise, what would have happened if there was an edge from 2 to 6? To be precise, when we explore F from 5, wait, 1, if there was an edge from 2 to 6, what would have happened? The neighbors of 2 to 6, of 2, okay, let me just think. Let's think what would have happened then. We would have gone through all this to process. When we looked at 5's neighbors, it didn't see anything new. When we went to 4's neighbors, it didn't see anything new. When we got to 2, right, because now this is only adjacent to 2 and 6. So when we expanded 2, okay, the edge would have been down. Any questions about it? Okay, I may have gotten a little confused, but right now, does everybody see what I'm trying to say? In any graph, if it's an undirected graph, every edge is either going to be a tree of discovery edge or it's going to go back to an ancestor. Okay? There cannot be a forward edge from this vertex down to here. Why? Because when we had this vertex and we looked at all of its neighbors, did everybody see that because we immediately shift attention on discovery? This edge from 1 to 5 is in the adjacency list of 1. When the recursion gets back from 2, it's going to process that edge 1, 5. But the recursion 5 is going to clear through all of its neighborhood before it gets its attention back. So the edge is going to be a back edge and not a forward edge. Any questions about that? Yes? Is 1 a child of 5? 1 is an ancestor of 5. The way to think about it is, the tree edge is this, 1 is an ancestor of 5 because there is a path going back in the tree from 5 that eventually gets to 1. So we say that 1 would be an ancestor of 5. Yes?
Why does 5 go to 2 and 1 but not 4?
Why does 5 go to 2 and 1 but not 4? Okay. 5 go to 2 and 1 but not 4. The reason is because when we, in this discovery, it went from here, oh, I discovered that, oh, I discovered that, oh, I discovered that, oh, I discovered that. The edge from 5 to 4 is a tree edge, right? Every edge is going to get labeled, in the graph is going to get labeled by what was its role the first time we saw it, right? So the edge 4 to 5 is a tree edge, okay? Does that answer your question?
Okay. Why does it have edges to 2 and 1?
Why doesn't it have an edge? Why doesn't it have an edge from 2 to 1? Because the edge 1 to 2 is a tree edge. Okay.
Why does 5 have edges 2, 2, and 1?
Why does 5 have edges? 5 has an edge to 1. 5 has an edge to 2. Does everybody see that? 5 here. What's the degree of edge of 5 in the tree? In the graph, it's 3, right? In the tree here, okay, 5 has 3 edges. 1 going into it and 2 of them going out of it. Does everybody see that? So if this is correct, okay, the degrees here should be the same as the degrees there. What's not happening?
Based on the code that you had, like 1 and 2 were already discovered, so why would 5 go to 1 or 2? Just return. There are no more undiscovered.
Okay, so what's happening? We went from 1, we discovered, 1 was initially discovered but not completely processed yet, right? We go out to this thing. When we had this, we discovered this, immediately we did a depth-first search from here, a recursive call. That meant that it interrupted what it was going to do on these to start working here, right? When we look at the neighbors of 2, well, we could say, well, the neighbors of 2, well, there was vertex 1, but that's already been, we've already used this edge, right? So we already know the classification of that edge. But vertex 2, edge from 2 to 3, wow, we discovered somebody. So that's in the tree, and we're now recursively shifting our attention there. So the point with depth-first search is that we're not completely processing vertices before we leave them. Okay? The moment we discover something, we're jumping and switching our attention there. Okay? Look at the code again. Maybe this will make it clearer. See what is happening? Whenever we discover somebody, okay, we process the edge, maybe classify it, do what we want with that edge, and then immediately do a recursive call to depth-first search from that new vertex as source. And now we're going to explore the graph from that vertex's point of view. And only once that is finished will that recursion come back. And we will continue looking at the neighbors of B. Yes? I don't perform a recursive call on a back edge. I only perform a recursive call when I discover something. Whenever I discover a vertex, I'm going to do a recursive call from it. That's exactly right. Any questions? Yes. Oh, yes.
So from vertex 2, how did you decide that you're going to go to 3 first instead of 5? So would there be a separate tree if you discovered 5?
So the question is, you're saying, how did I decide in this case whether I went to, so I'm exploring vertex 2, and I had a choice of going to 1, 5, or 3. Why did I go to 3 first? I'm assuming in this case, I guess, that the adjacency list is ordered by vertex size, by vertex number. And if so, 3 would have appeared on the adjacency list before 5. Does everybody agree with that? But what if that wasn't so? What would my tree look like? Let's maybe do that as an exercise. Let's say that everything is in sorted order on the adjacency lists, except 3 and 5 are reversed. What would my tree look like? Okay? And I may need some help doing this dynamically, but let's see what we can do. We're going to start on vertex 1, and from vertex 1 we're going to look at our outgoing edges, and 2 is the lowest ordered one from 1, right? So boom, I discover 2. Now I'm going to focus my attention on 2. 2 goes to 1, but no, 1's been discovered, so that edge has already been dealt with, right? Now from 2, you tell me the next one is 3. Great, I'm going to discover vertex 3 now, right? And from vertex 3, what am I going to discover? I could go back to 2, but that's a parent, so that's not already been used. Now I discover 4. Does everybody see that? And looking at the edges out of 4, there is the edge going to 3 and the edge going to 5. I've discovered somebody else now, 5. Does everybody agree that? And from 5, what are my outcomes? I could go back to 1, ka-chunk, that's a back edge. Where else could I go? I could go to 2, ka-chunk, that's a back edge. To 4, well, that one's already been I already accounted for that edge, right? So that's not a back edge. Now there's nothing to do from 5, is there? So now I go back to 4. What other edges from 4 are there after 3? I went to 5, no, nothing. I go back to 3. Is there anything to do from 3 yet? No. Anything left to do from 2 yet? No. Anything left to do from 1 yet? Yes, I can go down to 6. Does everybody see that? So depending upon the order of the edges on the adjacency list, my tree might be somewhat different. That's certainly true, but it will only have tree edges and back edges. Yeah.
Sorry, after you did 2, what would happen if you looked at 5 instead of 3?
What, now you want to make another change. What if after I had done 2, instead of doing 5, 3, I went to 5? Let's try to do that now. Okay, at the risk of doing it, let's try to do it again. I believe what you're saying is I would go from 1. I could have gone from 1 to 2 to 5. Is this what you're telling me? And now where do you want me to go next from 5? I could go back to 1, but that's a tree edge, right? I could go back to 2. I could go, back to 1. That would be there, right? Or I could discover vertex 4. Does everybody see that? And now from vertex 4, what could I do? I could go back to 5, but that's already there. Discover 3. Now 4 could discover 3. Does everybody see that? And from 3, going out of 3, what could I do? I have an edge to 4 and an edge going back to 2. Does everybody see that? Now, is there anything else to do from 3? Is there anything else to do from 4? Is there anything else to do from 5? Is there anything else to do from 2? Is there anything else to do from 1? Yes, there's 6 still. Does everybody see that? So what's interesting about this? I came up with different depth first search trees. But I don't care. What I do care is every single one of them, every edge was either a tree edge or a back edge. That's the property I'm going to care about. Yes? Okay, if I have a tree edge, you could think of when I go through it, when I look at it from here going back, that's the second time I looked at it. The classifications happen the first time I touch each edge, right? Well, you have a question? So now if you're adding, now you're changing my graph again. You're telling me there's going to be a edge from 6 to 7, and an edge from 7 to 2. Those are just edges in a graph right now. Until I do a search, they have no labels yet, right? Now, what's going to happen when I do that? Okay, if I can remember correct, pick my favorite tree. You're adding me edges that go from, you're adding me a vertex 7. with the property that it goes to 6 and it goes to what? 2. What's going to happen now? When I went back here, bunk, 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 now there is an edge from 2 to 7, right? So what would happen here is there would be another descendant from here going to 7. And 7 would then be the discoverer of 6. Does everybody see that? And now bunk, bunk, nothing else to do. Does everybody see that?
You can go from 6 to 1, right?
Could I go from 6 to 1? 6 to, okay, I see. There was an edge from 6 to 1. I would have processed it this way, and that edge would have been a back edge.
You previously said that you don't repetitively call a discovered edge, but if you went from 1 to 5, then back edge to
Okay, these are getting too complicated for me to keep straight. Okay? But what am I saying that is simple? The basic algorithm is simple. We're labeling edges the first time we are using it. Okay? An edge is either going to be a tree edge, meaning it discovered something, or it is going to go back to being an ancestor. Now, why is that? Okay? Because when I'm processing, once I've gotten to this, once I was at this vertex, I got interrupted. My attention wandered. Number 1 doesn't get attention back until after number 6 is done. Does everybody see that? So this edge is going to have to be labeled like that. Okay, yes?
So this always creates a graph isomorphic to the original, or just drawing it differently?
Well, first of all, we're not changing any of the edges. So you're right. If we remove the arrows and the labels, these are all just different drawings of the graph, right? Okay, it's the same graph. I'm just walking over it, right? We're describing one way that I'm walking over, and ordering, and the order of the vertices in the adjacency list tells me kind of how do I break ties of what do I do next. But the important point is no matter how you scramble up that adjacency list, when you finish doing the reversal, if it was an undirected graph before, every edge is either going to be a tree edge or a back edge. Okay? Any questions about that? Any questions about that? Why there are only tree edges and back edges? Why can't there be a forward edge, you're saying to me? Why couldn't there be an edge from here going down to that? Well, why not? Because if there was an edge between 1 and 3, what would have happened? It would have been first processed when we were exploring vertex 3, right? So it would have been a back edge, not a forward edge. Does everybody see that? Wait a minute, why can't we have a cross edge like that? Okay? Well, why not? Because as we discovered this thing, vertex 4 would be completely processed before vertex 6 was ever discovered, right? So what would have happened? It would have been the discovery of it, and it was a tree edge. Does everybody see that? And what about a cross edge going the other way? Why can't we go like this to this? Okay, well, this vertex was completely processed before this vertex ever came into being, right? So if there was, this vertex would have been a descendant of that. Any questions about that? Yes?
I get what you did with 6 and 4, but when you said, why can't there be an edge from 2 to 6, I don't get that.
Okay, if there was an edge in the graph from 2 to 6, what would have happened? We would have, assuming 2 was before 6 in the adjacency list, what would have happened? We would have gone bunk, 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 bunk. Now we would have processed the edge from 6, right? And 6 would have been discovered here, making the edge from 1 to 6 a back edge. Okay? Any questions about it? Okay? Yes?
When you're running through all your edges, do you have to run back up to your parent every time just to double check?
Well, what I guess what I'm saying is that in a course of a recursion, what are you doing? In a recursion, whenever we discovered somebody new, that pushed somebody on the stack, right? That pushed this thing on the stack and started searching here, right? Discover somebody new, it pushed it down here, it pushed it down here, it pushed it down here. So what does that mean? That means that whatever hadn't been explored from here isn't going to get explored until basically all these recursions have come back. Okay? Any questions about that? Yes?
Oh, so as it's here on that graph, I think 1, 2, 3, 3 looks at 1, even though it's already been found.
3 looks, what would have happened if there was an edge from 1 to 3? 1, if we went down in here, if we explored vertex 2 before vertex, if 2 was before 3 on the adjacency list of 1, we would have explored this, we would have explored this. 3 would be somewhere, 1 would be somewhere on the adjacency list of 3. When we did that, 1 was an ancestor.
Oh, yeah, so these non-depth first calls that we do, the non-recursive calls,
Yeah.
go from 3 to 1. Should we also have a non-recursive call from 3 to 2?
There's no, again, look at the code here for a second. There's only one recursive place in here where there is a recursive call. It is DFS. See, it's DFS. Up there, DFS is calling DFS over there, right? See in the discovered part? Up there. Okay? So whenever a new vertex is discovered, we shift the attention of our search. Okay? Otherwise, we just keep cruising through that loop that is going through the adjacencies of our current vertex. Oh, it goes back to somebody. Oh, it goes back to somebody. Okay? Any questions? Okay? So, the key idea of depth first search is that it organizes the edges in this nice way if it's an undirected graph. Any questions about that? Okay? So let's use and again, when you look at the code for classifying, look in the book, you'll see that it's telling whether or not what type of an edge you have. Okay, it's really just a constant time operation depending upon the status of these other vertices. The details I don't want to go through. I think if you go through it, it should be clear what is a back edge, what is not a back edge. Any questions? Okay, and this is basically the argument that I repeated to you. Let me give you an argument of an algorithm where doing a depth first search is better than doing a breadth first search. Okay, and it's a problem that comes up in a graph. How do you find a cycle in a graph? Okay, suppose I tell you, guys, here's a tree, okay, and do something for your homework on this tree. And suppose it wasn't a tree. How would you convince me it wasn't a tree? Well, you would show me a cycle in the graph, right? Suppose I have a graph that contains a cycle in it. How can I find a cycle in a graph? Let's go back to my example here. Here is a graph. Where is there a cycle in a graph? 1, 5, 4, 3, 2, 1 is a cycle. Does everybody agree? 1, 2, 5 is a cycle. 2, 5, 4, 3, 2 is a cycle. How can you take a graph and find a cycle in it? Any ideas? Yes.
So if you have a source code, you keep moving like recursively until you go back to the source code.
What you're saying is, if we start by saying, do a depth first search. What happens if you do a depth first search? What do we know about the graph if we have done a depth first search on it? Every tree has one of two properties to it, right? It is a tree edge, bunk, 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 or a back edge. Where do we have a cycle in the graph? Okay? I claim the moment we find an edge that is not a tree edge, it is going to be a back edge, right? If it didn't discover a new vertex, it goes to an ancestor of mine, right? So what is the cycle that we have identified? If we have a back edge, it goes from me to a particular ancestor. The tree defines a path from that ancestor down to me. Does everybody see that? The back edge plus the path in the tree between those two vertices defines a cycle. How many people see that? Okay. So to find a tree, if I have a depth first search tree, okay, all I need to do, the first back edge, the first edge that does not discover a new vertex, okay, that goes back, and once I then go from that vertex till I walk down in the tree till I get to here, that will give me my cycle. Any questions? So if I give you a graph with n vertices and m edges, n vertices and m edges, what is the time it takes to find a cycle in that graph? Yeah? You say, oh, n plus m. Is there a slicker way to say that? O of n. Do we have to look at all the edges in a graph? How many? What's the maximum number of possible edges we could have to look at that graph till we found our cycle? Well, at most n minus 1 of them could be in the tree of discovery. Does everybody see that? Discover, 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 discover. Once everybody's been discovered, you're in trouble, right? The next edge is going to create a cycle with somebody, right? By the time you look at the nth edge, you will have had a back edge. Okay? And that is enough to define a cycle. Yes?
Assume that the graph is more than n edges has a cycle.
Yes, if you tell me, hey, I've got this graph on n vertices and n plus 5 edges, it's a tree, what do you say? It's not a tree. Okay, it can only have n minus 1 edges, right? So if it has more edges than that, there's got to be a cycle someplace. And depth first search is going to find it. Because the moment you see a back edge, you have found a cycle. Does everybody see that? Now, is that true, by the way, with breadth first search also? That by the time you see the nth edge, you're also going to have a cycle? Who here says that by the time we look at the nth edge with breadth first search, we also have a cycle? Who here says yes?
Look at or discover a new edge?
Once we look at the nth edge, we will have seen a cycle with breadth first search. Who here says yes? Who here says no? The answer is yes, but it's complicated. Where is our cycle going to be? Remember, every edge was either a tree edge, right? Or it was a cross edge, right? If we have a cross edge, do we have a cycle? But what is that cycle going to be? It's going to be that edge plus the path to the root plus the path to the root. It's in more pieces, right? Does everybody see that? The depth first search laid out the cycles very, very neatly. Any questions about it? Okay, how much time do I have? I have 4 minutes, and I'm going to do something else unless you guys have questions. This is important to get this stuff down. Any questions about it? How does it look like to find the cycle with depth first, breadth first search? Okay. Basically, the algorithm to find the cycle is really going to be on a process edge. If I have an edge xy that I'm processing in the course of a search, if my parent is not, if the guy who discovered me is not x, okay, then that means I found the back edge, right? And if so, then the cycle is going to be, I need to find the path that lies between y and x, okay, and this edge plus that path is what defines the cycle. Any questions about it? So finding a cycle in a graph is a way to do this here. Any questions about it? Okay. Still got 3 minutes, and I'm going to annoy you. Any other questions on this? Can anybody think of a reason why you might want to find a cycle in a graph? Yeah? Okay, never mind. Any other reasons? Yeah? With web pages, again, you may or may not want to have a cycle that goes back to someplace else. Okay, that's, I guess, what you're kind of saying. I will say that, why do I sometimes find a cycle? Do you guys remember Eulerian cycles in a graph? How to, a tour that visits every edge and walks back to what it was? You guys know how to tell whether a graph is Eulerian if you took that discrete. What'd you do? You tested if every vertex was even, right? Is it true that if you have a graph where every vertex is even, it's going to be Eulerian? Is that true? I hear people nodding. The answer is, of course not. Why not? What about this graph? Does this graph have every vertex of even degree? But is it Eulerian? It's also got to be connected, right? So what if it's connected and it has every vertex is of even degree, right? Let's say I do something like this to it, right? Now it's connected and every vertex is of even degree, right? No, which one's not? 3. No. I added two edges to. Does everybody see what I did here? I had my Jewish star here. Ka-chunk, ka-chunk, ka-chunk. Ka-chunk, ka-chunk, ka-chunk. Does everybody agree? Even degree not connected? What if I now add this, this, this? Does everybody see now every vertex is of even degree and it's connected? Now if I want to find an Eulerian cycle of this, how do I do it? Actually find the cycle. Well, basically what I do is I go and I find a cycle in that graph and peel it off. And say I'm going to visit those 3 vertices in order, right? And I find another cycle, okay? And I'm going to say that whenever I'm at this point here, I'm going to go, if this is the second cycle, I'm going to go splice that cycle in. Repeatedly pulling cycles off is the key to actually building an Eulerian cycle, if you know about it. Any questions? Okay, so think about this. Think about about how the depth first search worked, and we'll talk about it next class.
So like in our course, depth